Hello everyone, I am the developer of the RendASCII 3D rendering engine for Python. This rendering engine renders to ASCII characters rather than pixels so that you can use it in a terminal window like this. Some people had expressed interest in me creating a tutorial for how to use the engine, and I thought that might be a good idea. I didn't do a great job of documenting how to use it, so this might be the best option. If you are interested in looking at the source code, I'll link to the GitHub repository in the description, and it's released under the MIT license, so you can use it for pretty much anything you want. And feel free to comment what you think of this tutorial. I'm obviously quite new to this, so let me know if I need to improve anything. And let me know if you liked it and if you're interested for more, because this is going to be a super basic overview of the engine. I'm not going to go over like game design or the graphics pipeline or graphics programming very much. Not that I'm really qualified to go over either of those and explain them to you, but if you guys express interest in this tutorial, then I might do some more in-depth ones in the future and develop some more sophisticated projects. So please give me your feedback, and with that, let's jump into it. Before we jump into any coding, we're going to need a 3D model to use. Right now I have Wings 3D open. That's a 3D modeling program. You can also use Blender or 3ds Max, whichever 3D editor you prefer. For this particular tutorial, you don't even need to use a 3D editor. I'll post a download link to this particular model in the description below. But the key to remember is that whichever editor you use, every face of the model you're making needs to be assigned a material that has a distinct diffuse color. The diffuse color that each face has is what we can map to the different ASCII characters. So just make sure that you, I guess, have some sort of convention when assigning colors to the different faces. I just use basic primary colors in black. And with that, we'll be able to write a color map. And now we're ready to jump into the coding itself. You can see here that I've opened my preferred Python workspace. I like to use some terminal windows with Vim. If you would prefer to use an IDE like PyCharm, that's completely fine, and you should still be able to follow this tutorial. You can see that I have created a new project directory called RendASCII tutorial, and that I have created a virtual Python environment within this directory. I use the pipenv virtual environment tool, but you don't need to create a virtual environment to follow this tutorial. I would just recommend it, as it helps you structure and keep track of your project dependencies. I have also transferred the tetrahedron model and material files to this project directory. We're also going to be creating another asset, a color map, so we might as well organize these assets before we do anything else. I will recommend a asset structure for you, but you do not have to use it. You can feel free to experiment and use a structure that you're comfortable with or that you think is better. I'm going to create a couple new directories. I'm going to create a parent directory called assets, and within it I'm going to make a models subdirectory, and I'm going to make a materials subdirectory, and finally I'm going to make a color maps subdirectory. So if we do tree, we can see that we now have an asset structure that we can organize our assets with. So I'm going to move the tetrahedron object file to the models directory, and I'm going to move the materials file to the, not the models, the materials directory. Then we might as well create the color map. We can choose which characters should represent which colors on that tetrahedron object we just looked at. So I'm going to go over here and open Vim, and then edit, assets, color maps, and let's just call it object.json. These color maps are in the JSON format. Each color map should get its own JSON file. This is quite simple. All you need to do is, for every color that appears in the material file, just map it to a ASCII character. So for instance, black appears in hex within that material file. So let's map that to a hashtag. Red also appears. Oops. So let's map that to a /. My mistake. Green also appears. How about we map that to a colon? And finally, blue appears. So let's map that to an asterisk. And that is our first color map complete. You can create multiple color maps for different types of objects or for the same object, and the RendASCII rendering engine lets you swap color maps on the fly to represent different effects in-game if you would prefer. For now, we're just going to stick with this one color map for the sake of simplicity, but in future tutorials we might get into a little more advanced usage. You'll have to pardon the constant jump cuts. I'm still trying to get the hang of this. Now we're ready to install the RendASCII rendering engine itself. And using pipenv, you can do that like so. Make sure you include the pre-tag because it's still in its alpha state, and it may remain that way for a while I work out the bugs. You could also install it using just pip, or you could build it from source if you prefer. I like to start an interactive Python interpreter on the top terminal window here, so I can test out commands, such as this one, to see if we did successfully install RendASCII. I can also open documentation here while I'm working on my code. Now we're ready to write our first Python file. Let's call it tutorial.py, and we'll put it in the root of our project directory. And since it is going to be our main file, let's put in the standard Python boilerplate. We'll define a main function. I'll put in a pass there. And then we'll check to see if the file was executed rather than imported. And if that was the case, then we'll call the main function. Now we need to handle some imports. First, I know that we'll need to import the math library. We'll also need to import os.path. These will come into play in a little bit. And then from RendASCII, we actually need to import the engine class itself. So we'll do from RendASCII.interface import engine. Now I actually like to import it as our engine, because when you're working on a game, sometimes you have multiple engines, like a physics engine, perhaps an audio engine, and the rendering engine, of course. So having them all called engine is not very useful. So I like to add in that R so that I know it's the rendering engine. I just realized now that you all can look at the bottom of the screen at that clock there to see exactly how much time passes between each of these jump cuts, so you know exactly how much of an amateur I really am. Now we should create some constants to help keep track of the asset directories we just created. So I'm going to set root directory to be os.path.dir name, and I'll pass it file. That gives us a reference to the root project directory that we can then use to define all our other references relative to. For instance, say we want to get a reference to our asset directory, we can do os.path.join root directory, and then we'll just pass in assets as a string, and then that will give us a reference to the asset directory we just created. I can also do one for the colormap directory using a similar line, except this time I put an asset dir and then color maps, because that is what we named the directory. Then we'll do one for model as well. This is a bit repetitive, so you'll have to forgive me. Asset directory, models, and then finally material directory, os.path join asset dir materials. Now, you don't have to do it this way. There are probably a million different ways you can keep track of directories. You could separate these off into a configuration file. That would probably be good convention. But for the sake of this simple tutorial, we're just going to keep them all in the main file here. Now we're ready to actually create an instance of the RendASCII rendering engine itself. So we'll go here to the main function. I like to call the instance of the rendering engine RE for short because I tend to reference it a lot, and keeping it short but memorable to some extent tends to be quite handy. So what we do is we call the constructor of our engine. Now, I failed to document the code well, so how are we supposed to know what parameters to pass to the constructor here? Well, that's why I like to open this interactive terminal over here. So I could do import RendASCII interface, and then I can get help on that package or module, I should say. Excellent. And you can see the engine class right there, which includes the constructor. We have the colormap dir parameter, sprite dir, model dir, and material dir, and then num workers. So it's quite handy that we just created all of those constants referencing our asset directories. I'll note that we're not going to worry about sprite directory because we're not using any sprites in this tutorial. The engine does support sprites though, although the support is quite buggy. So let's go ahead and put in colormap directory, and we'll set that to the constant we just created up above. We'll do the same for model directory. And then we'll also do the same for material directory. And since these are optional parameters, you can see like sprite directory has its default value as an empty string. We don't need to worry about assigning anything to that parameter since we're not using it. And then we probably won't end up changing what num workers is equal to, but I'll still include it just so I can explain it a bit. Num workers is the number of sub-processes used for actually rendering. Now you might be wondering, well, why is it 0? When you set this value to 0, the main process will simply not create any sub-processes to distribute the rendering to, and it will handle all of the rendering itself. Now I'd like to just put in a comment here before I forget, because I will forget. Rendering engine. I have to remind myself to write comments sometimes. So let's also write a comment for the next step, which is loading in the assets that we imported earlier, so the models, materials, and the color maps. I don't know why I'm using plural, there's only one of each. So we'll do importing assets. So to do this, if we go back to our help window, you can see 3 methods of the engine: load color map, load model, and load sprite. Those are what you use. So let's do RE. They don't return anything, by the way. RE.load color map. Now what's the first parameter? Color map name. Well, what does that mean? That is simply whatever you choose it to be. However you would like to refer to this color map going forward, when you create model and just model instances, you will use this key to choose it among all the other color maps. So I believe this color map we called it object.json, so let's just call it object. And then we need to pass it the color map file name, and that would be object.json. It already knows which directory it's in because of the parameters we passed to the constructor of the rendering engine class. Now we can load in the model in a similar fashion. So we have a model name parameter, and we'll call it Tetra. Just keep it somewhat short since we're going to be using it a lot. And then the model file name, that is tetrahedron.obj. Yes. Now, for better or for worse, I designed the engine so that it automatically loads in the corresponding material file for each model that you load, because in the wavefront OBJ format, the OBJ file references the material library within it, so you don't need to explicitly load it. I may tweak this in the future. I'm not super happy with how it works, but let me know if you have any better ideas, and post an issue on the GitHub perhaps. Next, we should create some instances. These include camera instances and model instances. Create render instances. I specifically call them render instances because they don't contain any physics information. RendASCII is not a physics engine. You'll need to keep track of all physics data on your own. You could also use an external physics engine like Chipmunk. I've had some success with that one, even though it's just 2D. Let's start with the camera first. I'll call the instance cam. So we'll do RE for our rendering engine instance. Dot create camera. Now, which parameters do we need to pass to this? Well, up at the top there you can see create camera. It has resolution, near, far, FOV, ratio, fog char, and culling. Hopefully most of those are self-explanatory. I'll still go through them. Resolution. So that's just an XY value pair, specifying the height, or rather the width and height of your sort of display area on the terminal, that is. I choose 50 wide and 25 tall because the font that I use on my terminal is approximately twice as tall as it is wide. So using those values gives me a roughly square viewing window. Next we have the near. This is the near viewing plane of the camera. So these are in units of length, but the exact meaning of the unit is arbitrary. It's up to you to define whichever units you want to use for your engine, whether it be meters or feet, whatever. That's what you should use here. The near viewing plane is how far that plane is from the focal point of the camera, and basically anything behind the near viewing plane will be culled. It's like a reverse draw distance. This is an engine technicality, and I would recommend setting it to some quite low value. In our case, that's, I think, 0.1 centimeters. I'll be using meters for length in this tutorial. Then we have far. That's more like your traditional draw distance parameter. So I'll keep that at 11 meters. That's fine. FOV, this is why we imported the math package, because we want to use the radians function, because the engine thinks in terms of radians, but I, and potentially some of you, think in terms of degrees. So I'll put in 80 degrees there, translate it rather to radians, and then pass that in as our field of view. There are no restrictions on what the field of view can be, so you can feel free to abuse the engine in that way. Next we have ratio. That's the aspect ratio. You might be getting more use out of this than you think because of the weird pixel shapes of a terminal window. Playing with the aspect ratio really helps you get it to look right. I know for my particular terminal that 1.5 is a value that makes it look fairly decent. Next we have fog char. That means any pixel that doesn't intersect with a polygon or a sprite will just have this default value. Makes sense to keep it as space. And then culling. Well, this could mean a couple things. In this particular case, it means frustum culling, but not including the near and far viewing planes. Culling will always occur on the near and far viewing planes, particularly the near one, or else you'll get some very bizarre graphical artifacts as a result of the projection matrices at the core of the engine. But this boolean controls whether the 4 other planes in the viewing volume, the frustum volume, whether culling occurs along those. And I give you the option to turn this on and off because my frustum culling routine is not good. It's horribly optimized. I think it generates excess polygons when it doesn't need to. It's in dire need of some work, and I do plan to work on it in the future. So for most cases, you should set that to false. There might be some rare cases where you might get a little extra performance if you set that to true, but I would be surprised. There's also backface culling in the engine. However, there's no way to turn that on or off, either on an individual model basis or on an engine-wide basis. I kind of regret that. I might give you the option to control backface culling if you choose, but for now it's just on by default. And before I forget, I also want to change that comment to be consistent with the tense of the other ones. Next, we need to create a model instance. So just like you have classes that can be instantiated, the model that we imported earlier needs to be instantiated before it will appear in workspace within the engine. Now, we only imported one model, but we could actually create as many model instances as we wanted, and they would all appear as separate sort of entities in the rendering that we will eventually get. However, we're only going to deal with one for now. And the rendering instance we'll call Tetra. And again, that won't contain any physics information, it's just the pure rendering information. So we'll do re.create model instance. If we take a look over there, below create camera, we see create model instance, and it has the parameters model name and color map name. These are the keys that I was referring to back in the import assets section. So we'll need to reference those now in order to construct our instance. So we'll do model name, that equals Tetra. And I'm getting that from up here. That's where we assigned that key to that model. And then similar deal for the color map name. We chose object, so we'll continue to use that key to refer to that color map. We are almost ready to render our first frame, but before that we need to update the transformations of these render instances we just created. For now we'll just worry about Tetra, because by default these render instances will both be at the origin, and since there's backface culling, that would mean the camera is inside the tetrahedron, and it wouldn't be able to see any of the faces because they'd all be culled away. So we'll probably want to move it in front of the camera a little bit. And this is where I should mention that RendASCII is a left-handed engine. It uses a left-handed coordinate system. That means that, let's pretend we're the camera for a moment, the positive x-axis would be facing in the right direction, and the negative x-axis would be on the left. The positive y would be going upward, and the negative y would be going downward. And then the positive z would be facing outward, going forward away from us, and the negative z would be going behind us. That's important to keep in mind because a lot of 3D modeling tools are right-handed, and that actually reminds me that the load model method of the engine class actually includes another optional parameter, if you can see here. Load model contains a right-handed, which defaults to false. I actually put this in explicitly for the purpose I just mentioned, and I forgot to bring it up, but it's important in our case. Since Wings 3D, the tool we use to create the tetrahedron, actually uses a right-handed coordinate system. So if we set right-handed to true, that will basically multiply all of the points within the model you load, multiply their x components by -1, essentially flipping them. I know it's not a perfect solution, but it might help you out in a couple cases. It doesn't particularly matter for something as simple as a tetrahedron, though. But let's go back down. We need to transform the tetrahedron. So how do we do that? Well, let's create a comment first, before I forget again. Transform instances. Call it render instances. What you need to do is take that reference to the render instance that we just created, and call setTransformation. And just for the sake of being thorough, you can actually see on the model instance class the documentation for all its methods. It has a hide, unhide, set color map, set transformation. Set color map is if you want to change which color map that model is using. So like say something gets damaged and you want to temporarily change it to a different set of characters to render as, you could do that. Hide and unhide simply determine whether or not the model is hidden in the engine. So you could have like maybe scene switching or level of detail using those two methods. But we're interested in set transformation. And it takes a transformation. And that means that it takes a matrix, a homogeneous transformation matrix. It uses row major order, so that means we're going to spend a little bit of time setting this all up. So I don't feel qualified to explain exactly what's going on with transformation matrices, but they're quite important to game development in general, and especially in rendering. I'm not going to apply any rotation on this transformation. We're just going to use it for translation right now, and I'll explain how we're going to do that after I finish typing it. I should probably just copy and paste these rows, but for whatever reason I feel like doing it all manually at the moment. And finally, the last row. 1.0. So there is a default like identity transformation matrix that doesn't apply any transformation at all. For those of you who do not know, the highlighted values here, these three, these represent translation. So the first one, the one at the top, represents translation in the x-axis, then the next one is in the y-axis, and then the final one is in the z-axis. So if you remember what I said earlier, the camera by default will be facing in the positive z direction. So that means we're going to want to translate this tetrahedron along the positive z-axis. And having played with this a little bit, I know that we're going to want to translate it about 1¼ meters. And for the record, this big group of 9 elements in the matrix, that represents the rotation. However, again, it's a little more painful setting rotation manually in a transformation matrix. I have a utility that will hopefully help make generating these transformation matrices way easier, so you never have to manually put them literally in your code like this. I'm just doing this to show you that you don't need to use the tool that I'm about to show you in a little bit. You can, say, use NumPy, and I think if you can cast its matrix to a list of lists or a tuple of tuples, then you could use all of its tools to create your transformation matrices, and then pass them to the set transformation function here on the render instances. Regardless, that is our transformation complete, so now we're about ready to move on to rendering our first frame. And to do that, we're going to need to call a particular method on the rendering engine class. So let's scroll back up and see which one it is. Well, there it is in the center, render frame. It takes a camera instance, an overlay, and asString. Let's start writing that. Render frame. Finally, yay. So it's going to return the frame to us. In this case, it'll return it to us as a string, but that's controlled by the asString parameter. So we'll do re render frame camera. So the camera instance that you pass to the camera parameter, this determines which camera's perspective the frame is rendered from. So say you wanted to set up some sort of split screen or like a little mini remote camera in the corner of the screen. You could have a couple different cameras in world space and use some manipulate the raw fragments that you get back from this method to compose them into your own frame and then print that. However, we're not going to worry about that. we're just going to pass the single camera we created, and overlay plays into that manipulation I was just talking about. It's a bit more of an advanced topic. I'll save it for a later tutorial if you guys like this one. And then as string, that's whether or not you get the raw fragments, pixel fragments back from the rendering engine, or whether it formats it into a nice string ready to be print for you. And we definitely want that in this case, so we're going to set that to true. And then we are ready to finally print it. It's just as simple as calling print, and then we go to see if I had any bugs in the script at all, which, spoiler alert, I didn't. In a previous cut of this particular segment, I already tested it and it worked, so sorry to ruin the surprise, but since we're in our virtual environment, we call Python 3, and that's the Python 3 of the virtual environment. But you could also, if you're using pip, use your system's Python binary. And if you're in an IDE, like PyCharm, I believe there's an option somewhere in the top row to run your script. You could even debug it. So we're going to punch in our script name and execute, and yay, it worked. Now you can see it was just a single still frame. It was almost more like a snapshot of our world space, our simulated world in there. So what you can see is that our tetrahedron did indeed get transformed 1¼ meters in front of the camera, and you can see we have a face of all asterisks. So let's, just for fun, go back to our color map that we created. The asterisk was mapped to the blue face, so that's the side that's facing us, just showing you the connection between the colors on the model and the ASCII characters you end up seeing. But the issue with this is that it's not a simulation or a game. It's a single still frame. We want like something dynamic happening. We want a real-time rendering happening. We want to see the simulated interaction within the world. And that gets a bit more complicated, but we will certainly get into that next. But for now, I think that wraps up this tutorial. We've already covered quite a bit of ground, and I don't want to go on covering more if no one's going to be interested. So just based on this already, I'd really appreciate some feedback. What do you guys think of both the tutorial and the rendering engine itself? So on the tutorial side of things, how was I? Did I talk too fast, or more likely too slow most of the time? Did I have any issues explaining anything? Feel free to ask me in the comments, and I'll try to answer as many questions as I can. And then on the engine side of things, the engine itself, if you'd like to submit any bug reports or make any suggestions, feel free to go to the GitHub repository and add them there. I'll try to make sure that all the proper permissions are set. So until then, thank you for watching. I hope it wasn't too bad, this first tutorial of mine. Let me know if you want a second one, and have a nice day.